Hello there. So this is video number 2 of section 4. What section is this? 4.4. So we've sort of introduced this idea of coordinate vectors for a vector in a vector space, right? And with the first example, we kind of got an idea for how we can always relate any vector space to Rn, right? And it was specifically by looking at this basis of size n and mapping out the coordinates or encoding the coordinates that gave us each vector when using a specific basis. I want to start now by first sort of looking at what happens when we study sort of this same idea but just restricted to Rn. So we ended last time sort of doing this, but I want to start with this example where we calculate this coordinate vector for a vector in R2, given a basis in R2. This defines sort of a nice matrix that we can study called the change of coordinates matrix. And then we will end by sort of proving the really sort of central theorem of this section, that in fact any vector space V that has a basis of size n and Rn, when we look at them as vector spaces, are kind of the same. So let's start off with this example. We, I think, ended last section with a similar example. But I want to sort of argue that we know how to do this in general, right? Because, I'll say, this problem, if we just had to guess the correct coefficients to go on B1 and B2, would in general be hard, but we have a way of not needing to guess. So remember, if we're looking for the value of the B coordinate representation of x, what we want, well, this is a vector of length 2 equal to C1, C2, where C1 and C2, again, are the coefficients needed to satisfy this equation. And remember that we know that these two coefficients exist because B is a basis for R2, right? And because these two vectors form a basis for R2, we know that there's some linear combination of B1 and B2 that can give us x. The question is, how do we find it? Well, notice that this is just a vector equation that we want to solve, right? So this is equivalent to solving the following matrix equation, whose columns are given by these basis vectors B, multiplied by C1, C2 is equal to x. And so this might be a little weird because we're used to x being here, and maybe this is poor choice of notation by the book and then by extension me, because I chose to use the book's notation, but we know how to solve this matrix equation, right? So to solve this, we just row reduce the augmented matrix. And so really, if we're given a basis for R2 and asked to find any coordinate representation of any vector, and actually we can extend this to Rn, we see that it's just equivalent to solving a matrix equation. And so now we can do some fun row reducing and, leave it to linear algebra to always somehow find a way to come back to row reducing in the end. Wonder if we were to make up a slogan for linear algebra, if it wouldn't just be, 1,001 ways to use your row reduction techniques. Maybe a slogan for calculus is like, we're going to teach you the really hard way to do derivatives, and then turns out there's a really easy way. I remember that. I was always annoyed by that like we learned the big limit definition and we had to work through all those limits. And then, after like a couple days of doing that on homework, they were like, oh yeah, there's just this, power rule way to do it. And I'm like, oh, thanks for telling us that after the fact. All right, so we've solved this. C1 is equal to -6, C2 is equal to 2. And so this gives us our coordinate representation of x, -6 and 2. And so remember, this means that, and you can calculate this, x is equal to -6 times b1 plus 2 times b2. And so this would just be the coordinate representation of x under this specific basis. And so notice again that we can now sort of extend this process to Rn. So if we were given a basis of n vectors in Rn, and remember we know that now that every basis for Rn has to contain exactly n vectors of length n. And so we were given those n vectors, we were given a vector x of length n, and we wanted to find the basis representation of this vector. We would just repeat this same process, but with a potentially higher dimension matrix. So it turns out this problem is just solving a vector equation. All right, so this matrix here, and before I erase it, which is the matrix whose columns are given by the basis vectors, actually has a special name in general. And so now I will erase it to leave me room. This is called the change of coordinates matrix from B to the standard basis in Rn. So I'll write out the full definition. So we're given some basis B that contains n vectors in Rn. And this might be, although this isn't my least favorite notation of all time, we're going to get to that later. We're going to let P sub B be the matrix whose columns are just these basis vectors. Then we say that this matrix P sub B is the change of coordinates matrix from B to the standard basis in Rn. All right, so I want to, for a brief moment, go over why we call it this and sort of how to interpret what this matrix is. And of course, now I realize that I actually do want the previous example. So let's look at this example, and I think sort of what's going on here will make more sense by looking at this example. So we're going to look at R2, where I've got B1, B2, and we'll use the same two vectors from before, 1, -2, and 5, -6. So then under this definition, notice I had pointed out this matrix before I erased it, put it back up, that the change of basis coordinates matrix, from B to the standard basis in Rn is just this matrix here. 1, 5, -2, 6. Again, the columns just match the basis vectors. So notice here, when we were looking at this vector x, which was equal to the vector 4, 0, and we calculated that the B representation of x is equal to -6, 2, I think it was. So again, notice that what we eventually showed was that P sub B times the B representation of x is equal to x, right? So this was what we observed in the previous example. So any single vector x like this, you can kind of think about x, right? So next, and I apologize, there's kind of a lot going on here. The standard basis, remember, for R2 is just the two vectors 1, 0, 0, 1. Right? So remember, this is the standard basis for R2. And so maybe we'll call this standard basis B sub 0. So notice that if I wanted to calculate the B sub 0 representation of x, this is actually just equal to x itself, right? Because 4 times this vector plus 0 times this vector is always going to give me the vector 4, 0. So you can kind of think of each vector, and this is a little weird and it always weirds me out. This is sort of just the standard basis representation of the vector x. Well, this is the new basis representation, right? So this basis representation of the same vector, right? So like we think about this vector as x, we can also just think about it as a specific basis representation of a vector, where now these two vectors are kind of the same, but just represented under different bases, right? That is that P sub B0, which is just the identity matrix times x, or times the P sub or B sub 0 representation of x is equal to P sub B times the B representation of x, right? So like each of these are just different basis representations of the same vector, and the change of coordinates matrix here, so P sub B and maybe even P sub B0, sort of give us what that vector is in the standard basis, right? And so ultimately this is equal to x. And so this is where the name comes from, right? Is the change of coordinates matrix from B to the standard basis in Rn, because we're sort of changing the coordinates with which we represent x. And what this matrix is doing is always changing those coordinates to the coordinates we'd get in the standard basis, which, as we see, is just kind of the same thing as x. So a little weird, but that's where the name comes from. And like, I think it provides maybe a little sort of background as to what's going on here. So you can think of these almost in a weird way as like kind of the same vector when we look at them like this, but just represented by different bases. So anyways, moving on from that nonsense. So the next thing we can notice in this definition, right, that because P sub B is the matrix whose columns are a basis, I claim that P sub B is invertible. And so I'd recommend actually pausing the video here and trying to convince yourself of this before I prove it. All right, so why is P sub B invertible? Well, notice that the columns of P sub B, by definition, are linearly independent. And so that actually just immediately implies, right, that P sub B is invertible by the invertible matrix theorem. So this implies by the invertible matrix theorem, right, because P is a square matrix with linearly independent columns. P sub B is invertible. So what does this mean? Well, this means for each vector x in Rn, we can also calculate the B representation of x in a fairly quick manner by just multiplying the original vector x by the inverse p sub b. Now, notice if we're just staying in Rn, this means that the change of coordinate map, right? So this means that the map that sends x to its B representation has matrix P sub inverse of B, right? So this linear transformation has corresponding matrix P sub inverse of B, meaning that this transformation is one-to-one and onto. Meaning that at least staying in Rn, this change of coordinates map basically just maps Rn to itself, but each vector is getting mapped to a unique basis representation that might be a different or the same vector. But the important thing is that this map, when we're working in Rn, so if I take a vector in Rn, take any basis in Rn, and use this change of coordinates map, which is defined by the matrix P inverse of B, this is a one-to-one and onto linear transformation from Rn to itself. But it turns out that we can actually extend this idea to any vector space V into Rn, and so this will be sort of the main result, and I'll talk about what that means and then sort of the definition behind it. So we've got this theorem. So we're going to take some basis now with n vectors, and now we're going to expand back out to any vector space V, not just Rn. All right. So then we know that the coordinate mapping of x to its B representation is a one-to-one and onto linear transformation from V to Rn. And so to prove this, we've actually already shown that this transformation is one-to-one. Right, so we showed that in the last video, right, that basically one-to-one is saying, well, if I have any basis, then each vector x has a unique representation under this basis, right? And so if two vectors have the same basis representation, then they're the same. So this is one-to-one. To see that it's onto, just pick any vector in Rn and consider, so maybe we'll say pick any vector V, which we'll define as C1 through Cn. Then notice the vector in B, right, which is defined by this linear combination, right? X is a vector in B. And the B coordinate representation of x is equal to V by definition. And so it's onto because basically for any vector in Rn, if I just line those coordinates up in order, I get some unique vector in V whose B coordinate representation is my vector little v. So it's one-to-one because if two vectors have the same basis representation, then they're the same. It's onto because any set of numbers will now give me a distinct vector in my space. And so in this way, V and Rn basically are, as vector spaces, kind of the same, right? So we showed that like this transformation is linear, right? That it sort of preserves how the operations work together. This transformation is one-to-one, so it assigns one vector to one vector, and it's onto, so it doesn't miss any vectors in Rn. So we have a name for this. And so we say that this means that V and Rn are isomorphic. And this just means, isomorphic means that there is a one-to-one and onto linear transformation from this space to this space. And so isomorphic in math basically means that in the context with which we're looking at them, they're the same, right? So certainly like the space P2 and R3, those two spaces aren't the same, but if we were to sort of look at them as vector spaces and ignore the, right, so like if you can imagine like looking at them just as vector spaces and not noticing the individual elements, right? So like one we're defining as polynomials, one we're defining as vectors, but if you were to just look at them as vector spaces, they would look the same. Because they would interact the same way. You can kind of think of one-to-one and onto as meaning like, I mean, they're both infinite spaces, but you know, because we can find this like one-to-one correspondence between their elements that matches all elements to a single other element, you know, they kind of have the same number of elements, but it's a little inaccurate since they're infinite spaces. And so, you know, this means that, again, like any vector space V with a basis of size n, it's secretly just Rn. So that's really cool. I think that's an awesome result. And it's always beautiful in math, I think, when we like define this new thing and, you know, we learn, oh, it's actually just this other thing that we've already seen. So anyways, next video, I'm just going to go through some examples of sort of problems that we now have the ability to do. They're actually already on the worksheet under video 3. I highly recommend trying all of them on your own before watching the video. You know, I think they give a lot of good insight as to like what we can do, and I think they'll be a little challenging, but certainly doable at this point. And then in the video, I'll go over the solutions to all 3 of those problems.